implies this B10 is convex. Suppose this is not convex. Can it be a non-linear space? बोलिए. Suppose the unit ball is not. Yes or no?
Yes, sir.
Correct. If it is not convex, how can it be non-linear space? If it is non-linear space, it is convex. Suppose it is not convex, how can it be non-linear space? It cannot be non-linear space, right? This is necessary condition. So if the ball is not convex, then it cannot be non-linear space. So let's take example. Let us take L half. Okay. I will take 2 here. Right, 2 elements. Huh? So X is X1, X2. Then what is the norm we want to define here? So we define this as mod X1 raised to P plus mod X2 raised to P. Okay. So this is P here. All right. I'm taking P equal to half. Okay. This is 2. Therefore, there are only 2 coordinates. So what is this ball of radius 1 with center 0? Set of all xy are x1, x2 such that mod x1 raised to p plus mod x2 raised to p is actually less than or equal to 1. Okay? Norm x less than 1 is same thing as norm x squared less than 1. Okay? So let us see what this geometrically. So I want to see what is this x1 raised to half plus x2 raised to half. Let me say y raised to half equal to 1. Earlier we had seen in the case of 2, x1 squared plus x2 squared equal to 1. That was a circle. Right? I want to see this ball here in L2, L half. So let me take x positive and y positive so that you don't get into this square root positive. What do you think this curve is? Huh? Let's draw the graph. Huh? This is 1. This is 0, 1. Okay. This point is on the curve. This point is also on the curve. So the curve passes through these 2 points. So let me call it as PQ. Okay. What do you think this curve will be like? Is it a straight line? Definitely not. So let us look at x1 raised to half equal to 1 minus y raised to half. I'm taking x1 less than 1 and y1 less than 1, y less than 1. Okay. So square it up. You get square of this equal to square of. What do you think this curve is? Answer your problem. Y squared equal to 4ax or x squared equal to 4ay. What is this curve? These are curves. What are these curves?
Parabola, sir.
Good. So this curve has to be something like this. Question is, why not this way? It won't be like this. It will be like this. Why you think? Now take this point and draw the graph. Then you have the midpoint here. Okay. That is half. And this is half. That is the point. All right. So now I am looking at, the whether this point is on the straight line joining PQ, whether it is inside this or not. If it is not inside, then it's not convex. Clear? So let us look at what is the
Yes.
status. So I have half, half. Okay. I take the lambda times P plus 1 minus lambda times Q. Now this lambda, I take it as half. Why I am taking half? It's easy for me to handle. Then this becomes half of P plus half of Q. Be careful, huh? What I am writing. I am writing in terms of. So this point will be actually half of. So what is the norm of this? It will be, 1/4, right? Plus 1/4. I have to apply this thing, right? What is the norm? Mod x1 raised to p plus mod y1 raised to p. P is half. So half squared, I have to take the square root. Again, half squared, take the square root. What do you get here? Half plus half, right? But you have two halves, right? So it will be 2 into this. It will be 2, which is not less than 1. Therefore, this ball is not convex. Therefore, this norm, half norm, is not a norm. Okay? That is the reason why you take always this P to be between 0 and 1. Okay? That's the reason why you always take 1 less than P less than or equal to infinity. For this, it's a non-linear space. But for 0 less than P less than 1, this LP need not be a non-linear space. Some sort of indirect proof. Is it clear? Is it clear or not? अरे बोलिए, हाँ बोलिए, ना बोलिए. Hello, Rishabh, is it clear?
Yes, sir. Clear, sir.
Why are you so quiet? Huh? Why don't you interact? Huh? ठीक है. So today's topic will be finite dimensional vector spaces. Only one lecture. Okay, I want to finish it today. And for this, I have to know some amount of some amount of what is called topology. Okay, so it's a very simple topology I'm looking at, not a very complicated one. So what it says is, again, recall, because I'll be using this in the proof, and therefore I don't want to rewrite again. Okay, recall. 1, let XD be a metric space. Then any compact set A in X is closed bounded. Easy to prove, okay? 2, if K be compact and F be a map from K to R, R or C, then F is bounded. That is, mod Fx is bounded by M for all X in K. This is second property. Third property, let X with an arm be a non-linear space. Then X going to norm X is a continuous function. Halfway I did this part. Okay. It's a continuous function. Okay. Now, if K is compact, then inf of Fx and supremum of Fx. This is X in K. This is also X in K. Exists and are finite. That means infimum of, suppose I call this as a some I, this as supremum as a yes, then I is less than or equal to f of X less than or equal to supremum for all X. Okay. Not only that, there is a point at which supremum and infimum will be attained. This is from metric space topology. Somebody would have done it for you. Okay. So I go back to this finite dimensional nonlinear spaces. The main theorem here is that if E is a finite dimensional vector space, then all norms are equivalent. Moreover, E is complete with respect to every norm. So every finite dimensional space, nonlinear space, is complete. Okay, and all norms are equivalent. Usually, to show that the norms are equivalent, what you show is that there is an isomorphism between the two spaces. So if you have two finite dimensional space of the same dimension, it's the same dimension, okay? Not written here, but it is the same dimension. What you do is isomorphism is actually a map which you take from one basis to another basis. That is what one does. So let us look at the proof. Suppose dimension of E is n. Some n is finite dimension. So let E1, E2, En be a basis. It always exists. Finite dimensional non-linear space, vector space will have a basis. Call it as E1, E2, En. Then for every x En, you can write it as a combination of E1, E2, En. So x equal to summation, I equal to 1 to n, xi I, ei. This xi1, xi2, xn is called the coordinate of the point x with respect to the basis E1, E2, En. That you know. Now you take Kn. K raised to n is nothing but either R raised to n or C raised to n, depending on whether you take K equal to C or R. Take a point xi in Kn. Okay. And suppose the coordinates are xi1, xi2, xin. Okay. So the xi1, xi2, xin, what we have here is actually they're the coordinates of the point x, and that coordinate of the points x are all either complex or real, depending on your vector space, whether it's real or complex. The coordinates are always from the field. The field that we are using is either real or complex. So given this x, you have the coordinate xi1, xi2, xin. Get this xi1, xi2, xin. You define t xi to be summation I equal to 1 to n xi I ei. Take this zi, whatever that coordinates you have. Then you define t xi equal to zi ei. For all xi1, xi2, xin, then this map is an isomorphism. That's obvious. It maps a basis to a basis, and therefore it will be an isomorphism. That is not a very difficult to see. It's 1, 1 onto is obvious and not a big issue. That's linear algebra. So now let norm E be a norm on E. So this initially we started with the vector space, non-linear space E. So let's call that norm as some two line E. Okay. Because of equivalence norm is equivalent relation, it is sufficient to show that the graph of T inverse on E is equivalent to this. That is what the point is about. How does T inverse exist? Because T is 1, 1 onto. Why it is 1, 1 onto? Because it is an isomorphism. Okay. It's a linear isomorphism. So by a previous proposition, which simple T inverse belongs to LDK, that's an obvious thing. If T is a linear map, then T inverse is also a linear map. I have to explain to you this. This you might have done it. Huh? Okay. So this is the next one. Let T be a map, say from E to F. EF are vector spaces, same dimension. Let T be 1, 1 onto. That is T is T inverse exist. Claim T linear implies T inverse is linear. Have you done this in your linear algebra? Rishabh. Rishabh, utho, jago, don't sleep. Huh? Yeah, are you sleeping or awake? Huh?
Sir, Rishabh went to admin block for some work, sir.
Huh?
Sir,
Rishabh?
Rishabh went to admin block for some work, sir.
Okay. This theorem has been done or not? If T is linear, then T inverse is also linear. Linear algebra. Hmm? If it is not done, you do it yourself. If you don't get it, I'll do it next time. Okay?
Okay, sir.
Yeah, why people have left the class? Huh? There are only 5 people. There are 11 people who are registered.
So we have already informed, but I don't know why others haven't joined.
What?
Sir, we have informed regarding your class that class is going on. I don't know why others haven't joined.
Hmm. ठीक है. All right. So what I was saying is that the map T inverse exists because it's 1 1 on 2. Why it is 1 1 on 2? Because it's a linear isomorphism. So you can, by the Cauchy-Schwarz inequality or whatever the inequality you have, or Holder's inequality, this norm of T xi will be less than or equal to norm of xi I, Ei by definition. Now apply triangular inequality, you get mod xi equal to 1 to n, mod xi I, norm Ei. This is the Holder's inequality I am looking at here. For P equal to 2 and Q equal to 2, it is summation I equal to 1 mod Ei square raised to half into mod I square. So call this whatever this sum I equal to 1 to n as C. So you get mod I into 2. This is true for all I in K. So we set C equal to this part. Hence T is a bounded linear operator and T inverse is also a bounded linear operator. All right. By the continuity of the norm, the xi going to norm T xi is a continuous map. That's what I told you in the beginning of the class. Okay. So since the norm is continuous, T is continuous, composition of two maps is continuous. Therefore, xi going to T xi is also continuous map from Kn to R. In particular, it is continuous on the unit sphere. Normally, in vector spaces, we work on unit sphere and then we can extend it to the whole space. Okay. So call that unit sphere. This is the surface of the unit sphere. Xi in Kn such that mod xi2. This is the L2 norm. Okay, equal to 1. Since S is compact, this is what I said. Any closed bounded set in Kn is compact, and therefore by the since the theorem xi going to T xi is continuous map, it attains its minimum on this set. So there exists a beta such that norm T beta is less than or equal to norm T xi for all xi in S. That is because of the minimality. Since norm beta is 1 and 1 is not 0, T is an isomorphism, and therefore we see the property of the norm 1, C definition. That implies that C is actually less than or equal to norm T beta greater than 0 if xi is not 0. So xi over norm, if xi is not norm 1, then xi over norm xi2. So we'll take the vector, divide by its length, then it will be of length 1. So it will be on S. Therefore, by this C less than or equal to TBE, we have C will be less than or equal to T of beta should be on the sphere. So this xi over mod xi square is less than or equal to E. So this mod xi squared is a mod xi2. Now L2 norm of xi is a real number and T is linear, it comes out. And therefore, this C times norm of xi2 is less than or equal to T. Therefore, T inverse is T inverse of X. So you can invert this xi. So you get T inverse of X in L2 norm is bounded by C inverse of norm X in E. Since this is bounded by C inverse 1 by C, therefore T with T inverse is continuous. So what we have got is both T inverse and T are continuous, and therefore on this arbitrary norm linear space is isomorphic to actually Kn or Rn with L2 norm. So you can prove the this if you take a Cauchy sequence in E, then you can show that this is also true. Since C inverse Xn is a Cauchy in Kn, then this will converge. So that also shows that this is true. So essentially what we have shown is that if E is a finite dimensional vector space, any finite dimensional vector space, then this finite dimensional vector space will be isomorphic to Kn with L2 norm. Any finite dimensional vector space. Okay. And not only that, since Kn is complete, this E also will be complete. So that is the proof that we have. Now what it says is that every finite dimensional non-linear space is closed and bounded, and therefore it's complete. Now let me explain to you what is the story that we have done. One minute, I'm saving. NIT Mizoram. This is 7, so this will be 8. Actually 9. Okay. So let us recall a few things. One, so we have two non-linear spaces, okay? E and F. T is a map from E to F, isomorphism. What does it mean? T inverse are continuous. T is 1, 1 or 2. 2. E isomorphic to F means that there is an isomorphism. Then set of all vector spaces okay, under this relation is an equivalent relation. That is E isomorphic to F, F isomorphic to G implies E is isomorphic to G. E is isomorphic to itself. E isomorphic to F implies and by implies F is isomorphic to E. So if T is the isomorphism, then T inverse is the isomorphism here. So it is an equivalent relation. Third thing, what have we done? We said that E be any non-linear space of dimension n. Then E is isomorphic to Kn. So if you have two vector spaces, EF of dimension n, because this is an equivalent relation, so E is isomorphic to Kn, F is isomorphic to Kn by the same theorem what we have shown now. This implies that E is isomorphic to F. That means that if E and F are non-linear spaces on F, then so EF non-linear spaces of dimension n, then E is isomorphic to F. That is, all finite dimensional vector spaces are isomorphic themselves. Kn complete implies that E is complete. The proof is simple. Okay. So this is through isomorphism. Through T and T inverse continuous. That's the theorem what we have shown. So essentially what we are saying is a finite dimensional vector space is same thing as Kn. There is no great difference. Okay. So that is the story which the theorem says. Uh, this is what this theorem, this is the Cauchy-ness talking about. So there are some useful consequences. Every finite dimensional subspace of a nonlinear space is closed and complete. Why? Because if you take any nonlinear space, if you take a finite dimensional vector space, it will be isomorphic to Kn or Rn, but Kn or Rn is closed and therefore this is also closed. Okay. So any finite dimensional subspace of a nonlinear space is always closed. Every finite dimensional nonlinear space is closed and complete. That is also a pass after. The third corollary is 10.3. If E and F are norm spaces and dimension of E is less than infinity, that is, it's a finite dimensional. Dimension of E is finite dimensional. Okay. So if T is a linear map from E to F, then T is bounded. Okay. That means if you have a finite dimensional space and a linear operator on that, whatever the range is, still the function is continuous. Okay. The proof is simple. What I mean is if E is finite dimensional and F is any nonlinear space, then any operator, any linear map from T from E to F is continuous. This is called automatic continuity. So if the domain is finite dimensional, then any, if you don't want any, every linear operator, so domain of E, and any linear operator T from E to F, any nonlinear space, is always continuous. This is called automatic continuity or automatic property. What I wish to tell you is that this sort of automatic property, you don't get it frequently. Okay. So that is what I wanted to tell you. The final theorem is that in Rn, you have high-numerical theorem. What is that high-numerical theorem? That every closed bounded set is compact. Same way, if you have any finite dimensional vector space, then A is compact if and only if A is closed and bounded. That's a simple proof. Okay. So it is exactly the metric topology we are doing here. Not a big issue, but you can read it yourself. Okay. So now we look at what is called some I'll see whether I should do this or not. I'll come to this point later. Okay, it's like almost orthogonal. It's called Riesz lemma. Okay, I'll come to this later. Then this is what the main theorem which we have proved now. 11.4 corollary. Let E be a non-linear space, then the following statements are equal. Dimension of E is finite. The unit sphere, closed unit sphere, okay, is compact. The unit ball in E is relatively compact. Every closed and bounded set in E is compact. This is actually virtually a theorem that you do using the what is called metric space topology. Since you have done metric space topology, so I will not get into this. Proof is simple. You can read it yourself if you wish to. Okay. So that is about the finite dimensional spaces. Right. I have to do what is called Riesz lemma. I will do that. Okay. I'll do it tomorrow. So let me stop for a while. Have any questions to ask? Sonam Kumari, Gangi Reddy. Pratnya, Saurabh. Any questions to ask?
No, sir.
No, sir.
All right. So I'll continue with the lecture. But this part of the story, I will be very, very brief. And I don't expect that I am expecting you to but in order to make sure that we understand okay, so let me see your syllabus if the quotient space is there. So this is the one of the things that normally you study in the structure of the nonlinear space, what are called quotient spaces. So you consider E to be a vector space and F to be a subspace. Then we define a relation where on E, we say that two vectors x and y in E are related, denoted by x tilde y, if and only if the difference x minus y is in F. So if the difference is in F, then you say that these two elements, x and y, are related. That's the relation we define. And we define bracket x as the element x in E, okay, such that the bracket x denotes the equivalent class. This is an equivalent relation. If x is related to y and y is related to z, then x minus y, okay. Should I write it? That this is an equivalent class, should I write it or leave it? Let me know quickly. E and F. Okay, I have some space here. All right. Why it is equivalent relation? You have E to be a nonlinear space, F to be some subspace. So take two elements x, y in E. You say that x is related to y. This is definition. If and only if x minus y is in E. Okay. Now x minus x is 0. It will be in E. Therefore, x is related to x. Why? Because it's a subspace. ERF. Okay. X minus y in F implies that y minus f, y minus x is in F. That's obvious, okay? Because F is a subspace. Therefore, this relation is symmetric. Okay. Now, x related to y related to z. This means x minus y is in F. This means y minus z is in F. This implies that x minus z is in F because F is a subspace. So if an element x is there and y is there, so this shows that this relation is transitive. That means what? This relation is reflexive, symmetric, and transitive. And therefore, this relation is an equivalent relation. Since it is an equivalent relation, it will create a partition, right? What are called the cosets. That is what he writes here. So let x be the coset defined by the point x in E. So bracket x. And what is this E slash f? E slash f is called all the cosets for x belonging to E. So for whatever x E, take the coset. Take all such cosets. That coset is called E by f. It is called the quotient. This is in algebra, it's called the quotient space of E modulo f. Okay, this E slash f, normally called as the quotient space of E by f. If you don't want to say by f, you can say quotient space of E modulo f. So this is a new space we are defining. On this new space, what we do is we induce two operations, plus and multiplication. So how do we add two cosets? If you take coset x and coset y, then you define this to be the coset generated by x plus y. That is a plus addition on the set E over f. How do you define scalar multiplication? Alpha times x is the coset generated by alpha x. Then these two maps, plus and the scalar multiplication, makes it a vector space. Okay. So with these two algebraic operations, this E over F becomes a vector space. Standard thing that you want to have done it in linear algebra. If you have not done it, I am doing it now anyway. So it is easily verified that these operations are well defined, obviously. No problem. Okay. If E is a non-linear space, now I am getting into function analysis. Instead of a vector space E, suppose E is a non-linear space. Then I would like to define a norm on this, the quotient E over F. How do we define it? So you define norm of x, norm of a quotient E F, this is the quotient norm. You take the distance of x minus z for all z in F. So take any z in F and take z in F and look at the norm of x minus z. Take the infimum. Get this infimum, whatever the 12.1 definition, that gives you a norm. This is a good definition since this definition is gives you one thing, that the quotient norm is less than or equal to norm x in E, and also it's a natural thing that E going to EF. So the natural map is what? if you take an element x, then you would like to go to the quotient space by the quotienting. That is alpha x. This is also continuous. That also you can see it. So there is a bit of geometrical interpretation here. So if E is a non-linear space, then E over F is a non-linear space with the norm, if and only if it is a closed space. So whatever the norm we have defined, whatever the two lines we have defined here by 12.1, whether it is a norm or not, that we have to see. What do you mean by norm? It has to satisfy the triangular inequality and two more, whatever the properties is. So if E is a non-linear space, and if F is E over F is a non-linear space, whatever the norm we have defined here, if and only if F is a closed subspace. That's what I was telling you in the beginning. That when you do group theory, you also define the quotient of a group. But a quotient of a group is defined E over G, G over E or something, even only if the group E is normal. So here, instead of normality, we are taking the closed subspace. So this is one very interesting theorem. Now, what I will do is I will not look into the proof of this theorem. I will also take out this proof from your syllabus. So I won't ask this proof in the examination. But those who are interested in understanding the nonlinear space, you read it if you have time after the midterm exam. So this norm that we have defined here by 12.1, whatever the number that we have defined by 12.1, it's a norm if and only if F is a closed subspace. That is the moral of the story. Proof is not difficult. It's little lengthy, okay. That's why I'm not doing it. And this norm is also called a closed. It's also called a quotient norm. Okay. So now we have some few theorems here, which perhaps I will do it next time. Okay. Now let me ask you a few simple questions. First question is that your exam is on 18th. Okay. So would you like to have a revision on Thursday? Questions for the exam will be whatever I have done till today, except the proof of the quotient spaces. All right. Would you like to have a revision on Thursday, or shall I continue with the lectures?
Sir, revision if possible.
So what you do is, if you have any questions to ask, you write it out on a piece of paper and you can ask me. I will answer those questions, or otherwise I will revise. Okay?
Yes, sir.
Have a good day. It's 12:55. Bye.
Thank you, sir. Bye, sir. Thank you, sir.
Bye.